An idealized satellite can repeat this circular path around a spherical planet. Gravity pulls toward the planet during the entire orbit, so the satellite has an inward acceleration even while its distance from the planet stays constant. How can inward gravity keep bending the path without carrying the satellite into the surface? We can isolate the deciding variable by returning to one launch point and changing only the sideways speed. The probe is unchanged. The launch point is unchanged. Inward gravity is unchanged. Only the sideways speed changes. Which launch hits the primary, which launch closes into a circle, which launch escapes and does not return? Assign all three outcomes now.
The slow launch should hit the primary, the middle launch should circle it, the fast launch should escape from it.
Release all three probes. The slow probe bends inward until the primary intercepts its path. The middle probe keeps missing the surface and returns to its starting point. The fast probe bends, but it leaves the frame on an unbound path. Their launch speeds are 0.65, 1, and 1.5 times the circular speed at this radius. Every amber arrow still points toward the same center. Only the initial sideways velocity changed.
Gravity keeps changing the middle probe's velocity toward the primary. Why does its distance from the primary not steadily shrink?
In this circular case, the probe's velocity is sideways, tangent to the circle, at every point. Gravity supplies an inward change in velocity that turns the next tangent without creating a steadily inward velocity. To see that geometry rather than rely on a slogan, we will compare the velocity vectors across one very small interval. Freeze the circular probe at the launch point. Its blue velocity is tangent to the circle, while its amber gravitational acceleration points toward the center. Now let one short interval pass. The probe moves forward, and its next velocity is tangent at the new point. The two velocity arrows have almost the same length, but they do not point in the same direction. Translate both velocity arrows without rotating them and give them a common tail. The arrow from the old tip to the new tip is the change in velocity during this interval. It points inward. Add that inward change to the old tangent velocity, and the result is the new tangent velocity. Gravity does not replace the sideways motion. It turns that motion a little at every step. Resume the orbit and follow the arrows around one full circle. The velocity direction changes continuously, so the probe is accelerating continuously. However, the amber arrow remains perpendicular to the blue arrow in this circular special case, so the speed gauge stays constant.
Acceleration can therefore change the direction of velocity without changing its magnitude.
That statement is correct for this circle. On a non-circular orbit, gravity is not always perpendicular to velocity, and the speed can change as well. Draw the separation vector from the primary center to the probe. That vector points outward. Gravity points in the opposite direction, so the acceleration law needs a minus sign. As the probe moves, this separation vector rotates, and the gravitational acceleration keeps aiming toward the same center. At radius 1, call the acceleration magnitude 1 unit. Move the probe to twice that radius. The inverse square law reduces the magnitude to 1/4. On screen, the separation vector supplies the direction, while its length in the denominator leaves the required inverse square magnitude. The resulting vector law calculates the acceleration at every position. The gravitational force contains the probe's mass as one factor. Newton's second law divides that force by the same probe mass to obtain its acceleration. Those two factors cancel. In this test particle model, changing the probe's mass does not change its gravitational acceleration from the same position.
Does the primary really remain motionless while it pulls on the probe?
That is not exact. A true two-body system moves both masses around a common center. We hold the primary fixed because its mass is much larger than the probe's mass. We also model the exterior of a spherical primary as though its mass were concentrated at its center. Those two assumptions define the gravity model used by every path in this episode. A circle adds one geometric requirement. Compare two nearby positions separated by a small angle. The probe travels a short arc length during the interval. Its velocity vector rotates through the same small angle. The triangle formed by the two radii has the same shape as the triangle formed by the two velocity vectors. The similar triangles say that the change in velocity divided by the speed matches the arc length divided by the radius. The arc length is the speed multiplied by the short time interval. After dividing by that interval and letting it shrink, the required inward acceleration is the speed squared divided by the radius. This expression describes the curvature requirement. It does not introduce a separate interaction named centripetal force. Gravity supplies inward acceleration with magnitude the gravitational parameter divided by radius squared. Circular geometry requires inward acceleration with magnitude speed squared divided by radius. For the same amber arrow to satisfy both descriptions, those two magnitudes must be equal. Solving that equality gives the circular speed as the square root of the gravitational parameter divided by the radius. A more massive primary requires a larger circular speed. Farther from the same primary, the circular speed is smaller.
That smaller speed now makes sense because the larger circle turns more gently while gravity is also weaker.
That is exactly the balance. This equation selects one circular speed, not every possible orbit through that point. Return to the original launch point and the circular speed. Now increase the tangent speed by 15%. Must this faster probe escape, or can gravity still bring it back on a wider bound orbit? Commit to one outcome now.
I predict that it escapes. The circular speed already seems like the largest speed that gravity can bend into a closed path.
Run the probe at 1.15 times circular speed. It moves outward, slows, and returns in a wider ellipse. The committed escape path was plausible, but circular speed is not the escape boundary. At 0.85 times circular speed, the probe follows a smaller bound ellipse. At exactly circular speed, one special ellipse becomes a circle. At 1.5 times circular speed, the probe is above the ideal escape threshold and does not return. At this launch radius, that threshold is the square root of 2 times circular speed. The slower 0.65 launch hits only because its inward ellipse crosses the declared surface. A slower launch can remain bound without striking a sufficiently small primary. Now restore the exact circular initial state and keep the gravity law unchanged. A course forward Euler update pushes the computed path into an outward spiral. Using the same time step with a time-centered velocity Verlet update leaves a nearly circular path through this finite comparison. The physical model did not change. The numerical method changed. The energy error traces expose the difference more clearly than the artwork alone.
A nearly closed path is still not proof that the calculation is accurate.
That caution is essential. We still need step refinement and quantities that the physical model says should remain fixed. For this central force orbit, angular momentum and energy are the most direct ledgers. In the next episode, total momentum joins them when we widen the system to isolated collisions. Keep the same primary and the same circular model. Move the launch point to 4 times the original radius. What must happen to the circular speed? Does it double? Does it stay unchanged? Or does it become 1/2 as large? Choose the scaling now.
The circular speed should become 1/2 as large, multiplying the radius by 4 places a factor of 4 under the square root.
Substitute 4 times the radius into the circular speed equation. The square root turns that factor of 4 into a factor of 2, so the outer velocity arrow is 1/2 as long. Run both circular orbits for the same elapsed time. The inner probe completes 2 full circles, while the outer probe advances only 1/4 of its circle. The outer circumference is 4 times longer, yet the outer speed is only 1/2 as large. A full outer orbit therefore takes 8 times as long.
The same equation predicts both the shorter velocity arrow and the slower orbital clock.
That is the transfer we wanted. The geometry and gravity now make a new prediction before the simulation runs. Return to one circular orbit. Gravity points inward, velocity remains tangent, and their magnitudes satisfy the circular speed relation. The force law specifies the acceleration. The initial state selects one trajectory. The numerical method turns that continuous model into a computed path. Atmosphere, non-spherical gravity, other bodies, and relativity remain outside this model. When a computed orbit drifts, we need quantities that tell us whether the change came from physics or from the calculation. The next episode builds those ledgers around a sharper event: two bodies colliding, bouncing, or sticking.